Hi, my name is Nick Borson. Welcome to C# Generics 101. In this video, I'm going to give an introduction to what generics are in C#, and then we'll demonstrate using a generic type, a generic collection that's part of the .NET framework, which is list of T. Then we'll demonstrate writing a generic method that sorts a list of T, or an iList of T. And finally, we're going to write our own version of the generic list class, our own implementation of that. And we'll start there with a naive implementation that works but performs very poorly when the list gets big. Then we'll go into some depth about how to estimate complexity using big O notation, which is a way of categorizing how an algorithm's runtime cost scales with the number of inputs. So that will explain why our naive implementation is very slow when the list gets very big. And we'll then produce a better implementation. And finally, I'll have a little perf demo that really hammers home why the naive implementation is much worse than the improved implementation. What then are generics? Well, generics in C# introduce the concept of type parameters. Now, of course, we've used parameters before. We've used method parameters, which are the values you pass as arguments to a method. But type parameters are a bit different. Instead of being values that are passed in at runtime, they represent types at compile time. So essentially, you can, if you have a generic class, for example, that means you can write one class that works with any number of different types, because that type is a parameter. And then when you use that class, you create a particular instance of that generic class that's specialized for a particular type. And likewise, you can do the same thing you can have generic classes, but you can also have generic interfaces, methods, and delegates. So for example, generics are extremely useful for collections of objects, like the classes in the systems.collections.generics namespace. And one of the most common is the list class, list of T. So because it's generic, you can create a list of int or a list of string. The list contains objects of the specific type. And yet, because it is generic, that list class was only written once. That generic class was only written once. There was just one generic class that works with any type. So you kind of get the best of both worlds. You get being able to write it once and have it work with any type, and yet also getting type safety, because when you create a list of string, it only contains strings. When you create a list of int, it only contains ints. When you get a value out of a list of int, you know at compile time that it's an int. You don't have to cast it from some base type like an object. If we didn't have generics, then a container type like this would have to either only work with a specific type, so you'd have to implement a separate class to hold integers and another class to hold strings and so on, or you could write a container that just holds object, which is the common base type of all types. But then you lose the type safety, right? You add something to a container of object, and it no longer retains that information of what type of thing it holds. And when you get something out of a container object, you then have to cast it to the actual type of the thing. So having generics gives you the combination of the flexibility of being generic across any number of different types, but still retaining that type information and giving you that type safety. All right, here I'm in Visual Studio 2022. And I'm going to demonstrate a simple program that uses the generic list class from the .NET framework. So if I hover over, so here we have a method, demo.run, which is in another module here in demo.cs. It's a static method. And we pass in, the method takes an iList of string. So iList is an interface, which is a generic interface of string. And the iList of string is implemented by list of string. So we create a list of string and we put the type name in the angle brackets. So this then is the actual type we're creating. This is the generic type, and when we specify the type parameter in angle brackets, we get an actual instance of the generic type, which is an actual class. We can then new that to get an object of that class, and we pass that object to our run method. And then we do the same thing with integer. The run method is overloaded, so we have a run method for strings and another run method for list of integers. So let's go ahead and take a look at our run method. I'm going to right-click on that and say go to definition. And here we are in the demo generics namespace. We have a class called demo, and I've defined a public static method called run that takes an iList of string. So the list class implements the iList interface, and that means that you can implicitly convert an object of type list to an object of type list of string to an object of type iList of string. So here we're taking the interface rather than the actual class, because that way, when we later create our own list type that also implements that interface, we can use this run method with both. We can use this run method with any list, with any object that implements this interface. Okay, so we have an iList of string, which we've passed in. We call the add method on our list to add a bunch of strings. In this case, we're adding the first two stanzas of Lewis Carroll's Jabberwocky poem, which is a nonsense poem. And but because the list is type safe, it's an iList of string, not an iList of integer. If we were to try calling list.add 10, for example, we would get an error because 10 cannot be implicitly converted from an integer to a string. So it is type safe. We can only add strings to it. So after we've added all the strings, then we have a for each loop. So this is an iList of string is enumerable. So we can use a for each loop to iterate over the objects in the list. So for each item in the list, we're going to initialize this variable item to that particular value. And then we're going to, in the body of the loop, we call console write line, so we'll just write the string. Then we have another overload of run. So overloading in C# is this idea that you can have methods with the same name, but that take different types of parameters. And the compiler will automatically pick the method based on the argument type. So list of string is convertible to iList of string, so it calls this method. List of int is convertible to iList of int, so it calls this method. So in this one, we simply add the numbers 10 from 10 counting down to 1 to our list, and then we output them in the same way. And likewise, we couldn't add a string to this list because it's a list of integer. So let's go ahead and run this program. I'm going to build it, and I'll hit Control F5 to run it. And we see that we've added all these strings to the list of string, and then we, in our for each loop, we iterated over those strings and output them to the console. And then likewise, in the second function, we added the numbers from 10 counting down to 1, and then in our for each loop, we called console.writeLine to output each of those numbers. All right, pretty simple. So we've seen a generic class, list of t, and we've seen how that generic class can implement a generic interface, iList of t, in this case, iList of int or iList of string. I also mentioned earlier that there are generic methods. So here I have actually gone ahead and implemented a generic method called sort. You can see that the run method that takes an iList of int is calling sort, and here the run method that takes an iList of string is also calling sort. But the sort method is parameterized. You see that when I hover over the tooltip, it's saying we're calling sort of string, and here we're calling sort of int. And in this case, it's deduced the type parameter from the method argument. So let's go up and look at the method definition, which is right up earlier in this file. So we've declared the method as public and static. Static meaning you don't have to have an object to call it on. You call it, it's not associated with a particular object. It doesn't return anything, and it is parameterized. It has a type parameter t, and then it has the method parameter list, which has type iList of t. So it's able to deduce the type of t from the type of list, because when we call it with a list of string, it knows that t must be a string. When we call it with an ilist of int, it knows that t must be an int. And there's an additional bit at the end here. We see this where t colon I comparable t. That means that we have a constraint that this method can only be called. We can only create an instance of this generic method. We can only create a sort of int or a sort of string, but we can only do that because int and string both implement the I comparable t interface. If we tried to call sort with a type that did not implement I comparable, we would get a compile time error. And just to demonstrate that, let's go ahead and try creating a list of object. So object does not implement that interface, so we'll say var obj list equals new list of object. Okay, and then we'll say sort obj list. And this time we get the red squiggle, we get a compile time error, and it says the type object cannot be used as a type parameter t in the generic method because object does not implement I comparable object. So that where clause limits where we can use the list, but the reason that's important, or limits where we can use the method, limits what types the method can be used with. And the reason that's important is because now within the method body, we know that t implements that I comparable t interface, and that means that we're allowed to call I comparable methods on objects of type t. And this is very useful because we're implementing a sort method. We need to know how to compare items in order to put them in the proper sort order. Now, I won't go into details of the actual algorithm here, but I'll just sort of shrink this down so you can look at the comments. You can pause and look at the comments if you are so inclined. Basically, we're doing what's called an insertion sort. It's a common sorting algorithm. And I will just mention that I picked this because it's a very simple algorithm to implement and understand and explain, but it is only suitable for smaller lists. If you have a really large list, insertion sort could take a long time because it is an O(n) squared algorithm. And if you watch to the end of this video, you will know exactly what that means. So we have our sort method. We're calling sort before outputting the results. So in this case, when we call run with our list of strings, we should get the strings all sorted. And when we call run with our list of integers, where initially we added them in reverse order, well, they should then be output in the correct order. Let's go ahead or in sorted order. So let's go ahead and run our program. And indeed, we see that the strings are all sorted. We get all the blank lines first, and then we have the lines with the apostrophe and the quotation mark sorted before all the other lines, which are then in alphabetical order. And likewise, when we sorted the list of integers, we got them in the numeric order. So that demonstrates creating a generic method. Well, we've created a generic method. Let's now try creating a generic class. We're going to create our own implementation of ilist of t. And I'm just going to call this class list1 because this is going to be we're going to end up creating a list2 as well. So let's add a class, and I'm going to call it list1. And it's created a list1.cs file for me. And now I'm going to have this, it's going to be a generic class. It's going to be list1 of t. And I'm going to implement ilist of t. All right, now here when I hover over this, it says that list1 of t does not implement all these interface members because, of course, we haven't done so yet. So let's go ahead and hit Alt-Enter, and it will give us the opportunity to implement the interface. So what this has done is just added placeholders for all the methods we need to add for this interface. Okay, so ilist of t has all these methods, and so we're going to have to implement all these methods in order for our class to implement that interface, methods and properties. So how are we going to implement our ilist of t, or implement our list? Well, we'll just implement it internally as an array. So we create a member, and we'll just call it m_items. Whoops, it has type t square brackets, and we'll just initialize it to an empty array. And for this initial implementation, okay, t0. So the 0 means that we're creating an array of size 0. So initially we're creating an empty list, so it's just going to be an array of size 0. And what we're going to do is we're going to implement the list in such a way that it every time we add something to the array, we simply, since an array cannot change size dynamically, we'll just create a new array of the desired size and copy all the elements from the old array to the new array and then add the new element. So I'm going to skip ahead a bit and show you a completed implementation. So here is the final implementation. I've implemented all the iList of T members. We see that the underlying representation is this mItems field, which is private to the class. So this is just the internal implementation of the class. And then what we expose to the users of the class is all the iList of T members. So we have an indexer, this property that takes square brackets allows us to use the array subscript operator to access elements of this list. So that is one of the members of iList of T. So the getter will just return the array element with the specified index, and the setter will set the array element with the specified index to the specified value. So value is a keyword in a setter of this kind that means the value that you're setting, or actually in any property setter. The keyword value means the value you're setting the property to. We have a count property that simply returns the length of the array. We have a read-only property, which will just hard code to false, because we allow this list to change. And then we have an add method, and I just implemented, so there's both an add and an insert method, and for simplicity, I just implemented implemented add in terms of insert, so we'll look at that later. The clear method just replaces the array with an empty array. Contains, the contains method, and I can hover over for usage here, determines whether the collection contains a specific value. Well, there's also an index method that searches for the value and returns its index if found and returns -1 if not found. So we've just implemented contains in terms of index of. Here's a copy to method that copies the list's contents to the specified array. We just implemented that in terms of array.copy or array.copy. And I'll get to the enumerator in a second. So iList of T derives from IEnumerable of T, and this is what allows it to be used with a for each loop. So the for each, so IEnumerable is a sort of a standard interface that means we can get an enumerator, and an enumerator is a temporary object that allows us to get each item in a collection one at a time. So the enumerator has methods like, well, we can see the methods now. So we've created this enumerator class. The class definition itself is internal. It's defined within our list class, and so it's internal to our list class. Nobody else can see this class definition. It's private to the class, but they can see the IEnumerator interface that they get back when we return our instance. So our enumerator just consists of the underlying array and then a current position in the array. And when you first create the enumerator, it's positioned before the first item in the sequence. So when we initialize the enumerator, we have a constructor that initializes the array, and then the index is -1. The current property returns whatever the current item is, and of course you can't really call that until we've advanced to the first item, but it just gets the item with the current index. And there are two versions of current. There's the generic version that is type safe, and then there's another version that just returns an object. So there's an older there's the generic enumerator, which derives from an older non-generic enumerator class that just where everything is just object. Dispose is a pattern in in C# that allows things to free resources when they're done. So you could have, if we had an enumerator that did something like opened a file or created database resources or something like that, dispose would automatically be called when we're done with the enumerator to promptly free those resources. But since we don't have any of that, our dispose does nothing. Move next simply advances to the next item in the sequence, or to the first item in the sequence if we're at the beginning, or if we're before the beginning. So to do that, we simply increment the index. And then it returns true if we're still inside the sequence, if we're not past the last item, and it returns false if we are past the last item. So here, if the index, if the result of incrementing the index is less than the length, then we know we're not past the end, and so we return true. And finally, reset goes back to the initial position. So there's our enumerator implementation. So we have a getEnumerator method. Farther down here, we also have another getEnumerator, which is the iEnumerator. It returns the non-generic version. And we see that the same class, it implements iEnumerator of t, but that in turn is based on iEnumerator, the non-generic one. So we can use the same class for both. Okay, so we looked at getEnumerator. Index of is where we search we try to find the index of an item with a specified value. So we simply use a for loop to iterate over the array. And if we find, we use the static object equals method to compare the specified item with the array element, and if they're equal, we return the index. And if we get all the way to the end without finding the value, then we return -1, because that's what index of does. Insert is where, this is kind of the meat of the thing. When we call add, we insert at the end, and we could also insert anywhere in the sequence. So we could insert at the beginning by specifying index 0, for example. So insert is where we actually add something to the array, and we can specify the index or the position in the sequence that it's the 0-based index that it's inserted at. So here is where we actually we create a new array, we copy the old items, and we add the new item. So to start with, we get the length of the existing array. We just set that to we initialize the variable c to that value. We make sure that the index is in range. So if somebody specifies an index that is not in range, then we'll throw an argument out of range exception. If we hover over insert, it tells us that that is one of the exceptions that this method can throw. Now we do allow an index to be equal to c, because when we add something at the end, we specify the index 1 past the last element. That's going to be the index of the new item. But we don't allow the index to be greater than the count. Okay, so we create a new array with a new count, which is going to be the old count plus 1. The new array is going to be 1 larger than the old array. We copy all the existing items from 0 up to, but not including index. So these are the items before the new item we're inserting. So here we use a for loop to do that. And we simply copy those from the old array into the new array. So the old array is m items. The new array is items that we created on line 98. Then we store the new item at index. And then we copy any remaining items that follow the new item. So starting at index and the old array, up to, but not including c, which is 1 past, which is the count, so 1 past the last item. So all those items, we copy them, but we copy them at, the index is I in the old array, but it's going to be I plus 1 in the new array because we've inserted the new item before that. And finally, our new array now is complete, and so we just replace the old array with the new array, and then we're done. And remove is quite similar. We have two remove methods. There's a remove and a remove at. So remove just finds an item, gets its index, and then calls remove at with that item, and it returns true if we found it and false if not. Remove at is a bit like insert, but in this case, what we have is an index of an item that we're going to remove. So we again get the old length. We make sure the index is in range. This time the index has to be a valid item. It can't be 1 past the end. We create a new array, which is going to be 1 smaller than the old array. And then we copy the existing items that precede the specified items, item, copy the existing items that follow the specified item, but we don't copy the item that we removed. And at the end, we have our new array that is that replaces the old array. And I already showed you get enumerator. So that is our new list class. So let's see our new list class in action. So here in program.cs, you see I've changed the calls to demo.run to create a list one of string instead of a list of string, and a list one of int instead of a list of int. If I run this program, let's hit Control F5, you see that we get the same output we did before. I removed the call to the sort method, so we're getting the items in the order they were added. Now our little demo method only exercised a small amount of the functionality of our list class, or our list one class. So to make sure that the other methods of the list class are actually correct, I wrote a little test class here, a little test method. So we have a class called test with a static run method, and it takes an ilist of int. So we can use this to test any ilist implementation. And the way this works is we assume that the list of t class in the .NET framework is correct. And so we create an object of that type as our baseline that we're going to compare our own implementation against. So, so this takes an ilist of t, and it adds a bunch of numbers, both to the baseline list, the one that we trust, and to the list that we're trying to test. And then it verifies that they have the same count. It verifies they have the same contents. So this is calling an extension method called sequence equal that just iterates over both lists, make sure they have the same number of elements, and make sure each of the elements compares equal to the corresponding element in the other sequence. We call the contains method for each list. Contains -1 should return false, or false in both cases. Contains 50 should return true in both cases, but we just make sure that both lists behave the same there. And ditto for index of, they should return the correct index, -1 in the case where the item isn't found. Then we remove some items. We remove the last item, we remove a non-existent item. So remember, these are specifying not indices but values. So we're looking for an item, a value 99, and we're removing the item at that index. We're looking for value 9,999, which should not be found. So in this case, remove should return false. But anyway, so in both cases, we expect both list implementations, the one we're testing and the baseline, to behave the same. Here we're removing what happens to be the first item and some other item. And then after all those removals, the two lists should still be equal. And then we try getting and setting some values using the indexer. So that's using the subscript operator, the array operator here. Here this is both getting and setting, because the plus equals operator is going to get the old value, add 1,000, and then store the new value. And we do that for both lists. And then we should expect that the item at that index is the same for both of those lists after doing so. And then we test inserting some new items at different indices, both at the beginning, or at the end, somewhere else in the middle, and at the beginning. And again, we verify after insertion that the lists are all the same. So we call go back to program.cs, here we call test.run, and when we run this, we find that our test implementation does indeed work correctly. Oh, I guess I don't need those breakpoints anymore. But in fact, yes, it exited with code 0. It didn't throw any exceptions, and so we know that that the list works correctly, at least insofar as we have tested it. So our list class works, but as we're going to find out, it is slow. At least when we have a large list with lots of items, it gets to be very, very slow. So the reason is we create a new array each time we add an item. And furthermore, when we do so, we have to copy all the previous items from the old array to the new array. And the cost, that is the runtime cost, the amount of copying, is going to increase for obvious reasons as the list gets bigger. So that makes sense intuitively. Let's try to think about that in a more quantitative way. So this goes into how we estimate the complexity of an algorithm. So in this case, the algorithm is just our add method for the list, where we add one item. And we can express that in terms of how big the list is. So when we add the first item, then the time is very, very short. We just store the item in the list. But when we add the second item, when we add item 1, we have to copy one item from the previous list, or from the previous array to the new array. When we add item 2, we have to copy 2 items from the previous array to the new array. When we add item 15, we have to copy the previous, the 16th item at index 15, we have to copy the previous 15 items from the old array to the new array. So the cost of adding one item is roughly proportional to the size of the list. And we just say it's proportional to n. Now, it's not an exact multiple of n, but the idea is, there's going to be some fixed overhead. There's going to be some fixed cost to just the function call overhead, and we have, some if tests in there and so on. But the idea is that as n gets bigger, especially as n gets very large, all those other costs kind of become insignificant, and the big cost is proportional to the copying that happens. And maybe we copy n plus 1 or n minus 1 items. Maybe we copy items and then we also store the new item, so that's n plus 1. Well, if n is a million plus 1 is not really much different than a million. So we can really just kind of simplify this to say this is on the order of n. And to do that, we use this notation, O, the big O notation, O of n. And we say that that means that the cost of this algorithm, in this case, adding one item to the list, is O of n, on the order of n. So what about the cost of adding the first n items? So we start with an empty list and we add n items. Well, our first intuition would be that if adding one item is O(n), then adding n items should be O(n) squared, that is n times n. And that actually turns out to be correct, but it's not as totally obvious as you might think, because adding the first item is because n isn't the same for all those items we add, right? Adding the first item is going to be O1, or really, if the previous size of the list is 1, then the addition is O1. If the previous size of the list is 2, the addition is O2, and so on. So the n is different. So really the cost of adding n items is going to be 1 plus 2 plus 3 plus 4, etc., up to n. It's going to be the sum of that series. It's not obvious that that's really the same thing as as n squared. But it turns out that the sum of that series can be expressed as with the formula. If you have the sum of the natural numbers from 1 up to n, that sum adds up to n times n plus 1 over 2. And that's kind of a neat way of seeing that. If you take, we can take like the sequence we see here of 0 to 15, and we can group them into pairs. So we take the first and last item, 0 and 15, pair them together. Well, we're looking at the natural numbers. So let's say we take the 1 and 15, we pair them together, and that is 16. Then we take the 2 and the 14 and pair them together, and that is also 16. The 3 and the 13 paired together is also 16. And it turns out that there are n over 2 pairs. So the sum of that whole series is going to be n over 2 times n plus 1, or n times n plus 1 over 2. So 16 in this case being n plus 1, and n over 2 being the number of pairs. But but as I said before, n plus 1 and n are pretty much the same when n gets big. And furthermore, we really don't care about the division by 2, because what we're interested in really is how the how the cost of the algorithm changes as n changes. And so if that cost is proportional to n, or if it's proportional to n over 2, then it's also proportional to n, right? So that's just a constant factor. So we could ignore the over 2, we can ignore the plus 1, and for purposes of big O notation, we can just say that this is O(n) squared. So let's talk a little bit more about big O notation. So why it matters is it tells you what happens when n gets big. So, for example, if n is 1,000, then O(n) squared is going to be roughly proportional to, the cost is going to be 1,000,000 times something, right? It's going to be proportional to 1,000,000. But if O is 1,000,000, then O(n) squared is going to be roughly proportional to 1,000,000,000,000. That's a lot. That's a million, right? Whereas if we're using an O n log n algorithm, for example, where log n is, in general, in this context, we mean log base 2 of n. Well, log base 2 of n is, log base 2 of a million is about 20, because 2 to the 20 is about a million. So for an n log n algorithm operating on an n of a million the cost is about 20 million. Well, 20 million is a heck of a lot better than a trillion. So it's not exact, but it does give you a pretty good idea of what the impact is of processing a large amount of data for a given algorithm. Now, if you want exact performance, you're going to have to measure anyway. So big O is really just an idea of getting, you measure to see how fast the thing is, but big O is a way of analyzing to see how that is going to change as you get to a large number of items. And because we're only interested in that kind of, we're not interested in exact results, then we really only care about, we could ignore constant terms and factors, and we only care about the highest degree term. So if we have, n plus some constant c, well, we ignore the constant. We just say that's n, right? We can simplify things. And likewise, if we have some constant multiplier c, if we have c times n, well, we can ignore that constant multiplier, just like we ignored the divide by 2 in the last example. And that's just n, because it's still proportional to n. And if we have something like n squared plus n plus c, well, as n gets really big, that n squared is going to dominate. The plus n and the plus c, they aren't really going to matter. So we just take the highest degree term, and that in that particular case, we can simplify it to n squared. So if we go back to our original implementation, our inefficient list implementation, can we do better? How might we do better? Well, what if we don't have to copy every time? And the way we can do that is if we allow the array to include some extra space at the end for new items. So that way when we add an item, maybe there's already extra space at the end of the array for it, and we don't have to copy. And that means that the array size at any given time might be greater than the item count. So when we implement this, we're going to have separate fields internally for the array size and then the item count, where the item count is less than or equal to the array size. Then when we add an item, we only have to reallocate if the array size is equal to the item count. If the item count is less than the array size, we can just store the item and increment the item count. So the question then arises, when we do reallocate the array, when we do grow the array or create a new array, how much extra space do we include? Well, one option that might seem fairly obvious would just be to grow by a constant amount. Every time we grow the array, we add space for 10 more items or 15 more items or 8 more items, whatever it may be, by some constant factor. The problem is that doesn't really solve our problem. And to just allow us to express this in a concise way, let's just say our constant factor is 2. So every time we grow, we increase the array by 2 each time. Well, compared to our original implementation, we only have to copy half as often. Half the calls copy to a new array, but half of them don't. So we've sped up our algorithm by a factor of 2, potentially. Well, that sounds pretty good, but remember the big O thing, right? Half of n squared is still proportional to n squared. So we ignore that constant multiplier, and we still have an O(n) squared algorithm. It doesn't really help us to get to it doesn't really get us out of this problem that a very big number is still a very big number, even if you divide it by 2. And that's going to be true, if we choose 4 or 8 or any constant instead of 2. That's not going to solve our problem. So the solution is, instead of increasing by a constant amount, we just double the size of the array every time. So every time that the array fills up and we need to grow it, we create a new array that's twice as big as the old array. Not some constant size bigger, but twice as big. And the reason that works is that we copy less and less often as we add more items. So the cost of adding, when we add up the cost of adding the first n items, ends up being, we copy 1, and then we copy 2, and then we don't copy again until we get to 4, and then we copy again when we get to 8. So it's going 1 plus 2 plus 4 plus 8, and so on, up until the last copy is going to be, some power of 2 less than n, right? So we can write this, instead of writing 1 plus 2 plus 4, we can say 2 to the 0 plus 2 to the 1 plus 2 to the 2, because these are all powers of 2 since we're doubling every time, up to 2 to the k, where 2 to the k is less than n. So the last copy we do is some power of 2 less than n. Well, like I said before, when we're doing the big O analysis, we could ignore all but the highest degree term, which is 2 to the k in this case. And we've already established that 2 to the k is less than n. So adding the first n items here is on. Instead of on, we've gone from an on squared algorithm to an on algorithm. That might seem like a bit of sleight of hand. Is that really true? Have we really gone from on squared to on? Well, let's take an example. Let's suppose n is 25. The number of copies then is going to be 1 plus 2 plus 4 plus 8 plus 16. And those first 4 items add up to less than the last term. The first 4 terms in that expression add up to less than the last term. In fact, it's always going to be 1 less than last term. So 1 plus 2 plus 4 plus 8 is 15, and then the last term is 16. So really, we're just kind of rounding in a way by ignoring those first terms and only taking the last term. And in fact, it literally is just rounding in this case, because we can write that sequence as 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the third plus 2 to the fourth. Well, writing that in binary notation, it's 1, 1, 1, 1, 1, right? Those are just binary digits, which is equivalent to 31 decimal. So we're just rounding that down. When we eliminate all but the most significant digit, if you will, which is the last term, we end up with 1, 0, 0, 0, 0. So we're just rounding down from 1, 1, 1, 1, 1 to 1, 0, 0, 0, 0. And for approximation purposes, rounding is perfectly acceptable. Okay, so we've seen that the cost of adding n items in our new implementation is on. How do we describe the cost of adding one item? What is the cost just of our add method? Well, it depends, as we've seen, right? Sometimes it's a constant cost, so we express that as O1 because we don't have to reallocate the array. But sometimes we do have to create a new array and copy all the previous items, so it's On. So sometimes it's O1, sometimes it's On. How do we describe that? Do we just have to say, well, it's On because that's the worst case? Well, sometimes you might care about the worst case, but usually that's too pessimistic. We really care about describing more of the typical performance. And we can express that by saying that it is amortized constant time. So the amortized analysis, what it does is it averages the running time over a sequence of calls. There are a lot more O1 calls than there are On calls. And we've already established that if we do n calls, the total cost is On. So what that means is that if we spread out those expensive calls, amortize them over all the calls we make, then the average cost, or the amortized cost, is just a constant. It's O1. All right, so here is our new improved list class, which I've very creatively called list2 to distinguish it from list1. So again, it derives from iList. It's mostly the same, or much the same as the old list class. But you notice that we now have two fields. The underlying representation now has two fields, which are the array of items and then the count. And as we already discussed, we need the count because the logical size of the list, the number of items in the list, can be less now than the size of the array. The size of the array, which is the amount of storage we have available to us, can include extra space, extra capacity for new items to be added, so we can add new items without having to reallocate every time. Okay, so what else has had to change to make this work? Well, here's our indexer property. This is mostly the same, except now we compare against the count rather than comparing against the array length. And that same change occurs in other places. So here the count property now returns the count rather than the array length. Now add is where we get to kind of the heart of things. So add is now implemented differently. We start by calling a new method, an internal method, private to the class, called ensure capacity. And what we do is we ensure that the capacity, and I'm using the term capacity to mean the amount of storage allocated, which may be greater than the number of items, greater than the count. So we ensure that the capacity is equal to count plus 1. In other words, we have enough room, enough storage allocated to add another item. So ensure capacity starts on line 41 here. So this is the, we're saying that the capacity has to be at least count. And we compare that with, so we compare the count with the existing array length. And if it's greater, then we have to reallocate. So that's the only kind otherwise we don't do anything at all. So if the count is greater than the existing array length, then we have to create a new array, and the size of the new array is going to be either the old array size times 2, in other words doubling, or the specified count, whichever is greater. So typically it's just going to be doubling every time, but if you were to call ensure capacity with some value even larger than double the size of the current array, then we'd use that. Okay, so we create the new array using a new t with new size, and then we copy all the items. We use a for loop to copy all the items from the existing array to the new array, and finally we we replace the old array with the new array on line 54. So that's pretty straightforward. So ensure capacity. So add simply calls ensure capacity, which in most cases won't do anything at all, but occasionally will reallocate. And then we store the new item in the array and increment the count. Now we're using the plus plus postfix operator. In other words, the plus plus follows the variable, and what that means is that the increment happens afterwards. So when we're using this expression to index into the array, we're indexing into the array using the old count. So we're storing the item at the index we're storing the item at is the old count, and then we increment the count. So increment after. So clear just sets the count to 0. We don't even have to change the array at all. Contains is the same as before. Copy to is the same as before, except that we pass the count instead of the array length. The enumerator is almost the same as before, except now we have both an array and a count. Again, because the count might be less than the array length. So the constructor takes both of those. And when we call move next, here we're using the prefix operator, so increment before. So we increment index, compare the resulting index with the count rather than with the array length. And if it's less, then we know that we're still inside the, we're not past the end, so we return true. Resetting is the same as before, return goes back to before the first item. Index of is the same as before, except again we're using count instead of array length. Insert is different than before, so insert now is pretty much entirely separate from add, but they both use ensure capacity. So insert first does the bounds check on the index. The index has to be, can be equal to the count, so we can insert just past the last item, but cannot be negative, cannot be greater than the count. That's the same as before. Then we call ensure capacity to again ensure that we have room for all the current items plus one more. Then we shift any items that are after the specified index to the right by 1, to the right meaning towards the end of the list. So this is creating a gap to make room for the new item. And we do that in reverse order, so starting at the end so that we don't overwrite any items. Then we store the new item in the list and increment the count. Remove is implemented in terms of remove at, same as before. Remove at is no longer has to create a new list because we never have to reallocate for this. So all we do is we first do the bounds check on the index. Then we shift any items after the specified index to the left, if you will, towards the beginning of the list, so to fill the gap. And then we decrement the count. So that is the entirety of our list implementation. So going back to our program.cs file, I've modified this to call our demo functions, demo.run, with our list2 class now. So we have our demo with our list of strings, and we have our demo with our list of integers. And I've also, remember we created that test function to verify the behavior after we create our list1 class, to have a test function to verify the behavior of the list by, here it is, adding a bunch of adding a bunch of numbers and then comparing it with what you get from the built-in or the standard implementation. So adding and removing, inserting, modifying, and so on. So if we run this, then our string demo produces the results, the same results as before. Our integer demo produces the same results, 10 counting down to 1, and we didn't get any exceptions from our tests. So our list 2 implementation is correct as far as we know, as far as we've tested. So correct is good, obviously, but we'd like to know if our list 2 implementation is actually any faster than our list 1 implementation. So far, you've seen a bunch of PowerPoint slides, but we're just kind of taking it on, we're just relying on our analysis to know that this class should be any better than the first implementation when we get to large numbers of n. So to verify this, I wrote a perf test. So this test takes a new list delegate, which I'll explain in a moment, and then each iteration of the test measures the elapsed time for adding some number of items to a list of integers. So we start the first pass, we add 100 integers, then we multiply that by 10, so the second pass we add 1,000 integers, and so on up to 1,000,000 integers. So for each test pass then we output the number of elements that we're adding. We get the start time, which is a date time object. Then we create a list using our delegate, which I'll get back to. We add the specified number of items, we just call add that many times. We get the end time, compute the elapsed time, which is a time span, system.timespan, and then we write the elapsed time. And by the way, when we write this line, such and such elements, we use console.write. Console.write differs from write line in that we don't write a new line afterwards, so this string appears on the same line as this string. So what about the delegate? A delegate is a C# type that represents a function-like object. Basically, it's a function object. An object you can call, like you call a function. And you declare it much like you declare a function. You have the keyword delegate, then you have the return type, in this case ilist of int, then you have the name of the delegate type, and then you have the parameters, just like you would declare parameters to a function. So this run method then takes a delegate that doesn't take any parameters and creates and returns a newly created ilist of int. So that's how we use it. And here on line 15, we invoke that delegate to create a new list for each test pass. So how do we use this in our program? Well, again, it's called, our function is called perf test.run. And this is expecting a delegate that returns an ilist of int. So we can use this lambda syntax. So first in parentheses, we take the arguments that we're binding to the delegate. Actually, no, these are values that we're capturing. We don't need anything for this, so we just leave that as empty. We use the equal sign right angle bracket, and then we have the expression that represents the code, the expression that gets evaluated by the delegate. The return value of that expression is the return value of the function. So in this case, we're going to start by we're going to first run this test with the built-in, the standard list type from the .NET framework. So we'll just say new list of int in parentheses, like so. And just to show what we're actually testing, let's say console.write line measuring list of int. Okay. And then we'll do the same thing for our list2 class. And then we'll do the same thing for our list1 class, which is the one we expect to be the slowest. So here's list2, list1. Okay, so there is our performance test. And since we're measuring performance, I'm going to change from a debug build to a release build. That means we're actually testing code that's been compiled in such a way as to optimize it as much as possible. So this is what you would normally want to actually ship and what you want to measure when you're measuring performance. And then I'll run the program. So let's see what we get. Okay, so measuring the built-in list class from the .NET framework, we get 100 elements. We have 239 milliseconds. I expect this number is higher than, is high because it's the first thing we've run, and maybe it's having to just-in-time compile the list thing. So there's a startup cost there that's being factored in. But then we get 1,000 elements is less than a millisecond, 10,000 elements, 4 milliseconds, 10,000 or 100,000 elements, almost a millisecond, and 1,000,000 elements, 421 milliseconds. So there's some pretty substantial variation there. Measuring performance is hard. Sometimes you get some noise in the signal, but still we see that the performance doesn't dramatically change as the number increases. So here's our list 2 class. In this case, first time we have about a millisecond. 1,000 elements, we have about 1/10 of a millisecond. Again, about a millisecond. Then it goes up to about 2.5 milliseconds for 100,000 elements, and 26 milliseconds for 1,000,000 elements. So yes, it's increasing, but it's not increasing by O squared or N squared. Here is the one that we expect to be bad, and indeed we're not disappointed. So first we have 1.5 milliseconds for 100 elements, then it increases quite dramatically to 6.6 milliseconds for 1,000, and then 183 for 10,000. So this is 10 times as many elements as this, so you'd expect it to be about 100 times as costly. It's not quite that, but it's in the ballpark. And then we have 100,000 elements. So again, you'd expect this to be about 100 times as costly as the one before, and indeed it is more than that. And then 1,000,000 elements. Well, if this was almost 10 seconds, you'd expect this to be 1,000 seconds, which is, I don't know how many minutes exactly, but probably more than I want to wait for. So you can see how choosing an O(n) squared algorithm really hurts when we get to a larger number of elements. If you only measured with 100 or 1,000, you might think, oh, this is pretty good. So having that sense of the algorithmic complexity is somewhat important. So thank you for watching my Generics 101 video. I hope that was a useful introduction to generics for you, showed kind of what they're for in C#, how they allow you to have the flexibility of writing one piece of code that works with any number of different types, while still preserving type safety and preserving that type information. And a very common and useful use of generics is for things like containers, like the standard containers in the system.collections.generics namespace, like list, for example. So using list was a good example, and we also explored writing a generic method that allows you to write one piece of code that can operate on different types, in this case a sort class. And finally, by implementing our own list, we got to do a deep dive into how you can, first of all, implement a generic class, but also the difference between a poorly performing class that doesn't use a good algorithm, and a much better performing class that does, and how to analyze that using this concept of big O notation and algorithmic complexity. So if you've watched to the end, thank you for watching this video, and I'll see you next time.